With that specification list in hand, we're ready to start coding our functions. I like to say that let's use our suffering and pain from the past to make today a little bit easier. Remember that we've already coded up a number of functions for our BLAS Level 1 library. Specifically, this is Basic Linear Algebra Level 1 operations, and we have a library of functions. Together in videos, we did dcopy and descale. For both of those functions, we had a driver to help us develop and error check. Instead of having to recreate the wheel, let's go ahead and just copy and paste as a starting point for our general matrix vector multiplication function. In this case, I'm going to choose the descale files that we wrote. I'm going to copy. Here I've created a new file called BLAS2 library. This is Basic Linear Algebra Subprograms Level 2. The general matrix vector multiplication operation is a level 2 operation. As we continue in the course, we'll get better at understanding what's level 1, what's level 2, etc., etc. We'll go ahead and copy those two files inside. And then remember, we have already kind of determined what the name of our function should be. So it should be double general matrix, no special structure. And we're going to do matrix vector multiplication, so MV. And then, of course, that's going to be the driver, which is stored as a script file. Here, we want the actual function file, so we're going to change that to dgemv. Next thing we're going to do is open those files and start changing the documentation. Remember, we're doing this really kind of slick thing where we reuse work from before, but then adapt it to our new context. In that process, the first thing I want to do probably is change the first line of our function file. We've got the name of our function file, which is going to be double general matrix vector multiplication. And we know already that this function is going to have a number of inputs: the transpose character, scalar alpha, matrix A, vector X, scalar beta, vector Y. We also already know that the dgemv function is going to perform matrix vector multiplication in one of two forms. First, y is equal to alpha times A times X plus beta times Y, or the same exact operation but with the transpose of A. And we can specify what type of data each input is. Alpha and beta are scalars, X and Y are column vectors, and A is a matrix. Now that we've got our desired title, the inputs that we want, and the output, we should of course check at the bottom that the last line of our function actually aligns with the name that we have. So in this case, it's going to be dgemv. That's the end of that function. Moreover, all of this description is from our previous function. We don't actually need that. We've specified kind of what we wanted to do up here. We're ready to kind of go to the syntax. Notice we're going to have two different values of syntax, which I've already kind of written for myself. So the first value is going to be, if I do not want a transpose, then the value of transpose is going to be a single character input, which is capital N. If I do want the transpose, that value of the input is going to be a single character input with capital T. And those are really my two options. Of course, the inputs that we're going to use are not the ones that we had for our descale function, so I can actually delete this. And what we'll do is we'll actually run through each individual input separately to remind ourselves what we want from those. The first input we want is going to be the transpose input, which is going to be stored as character data. That input is going to specify if we want to calculate using the transpose of the matrix or not. There's only two separate options we're going to allow. One of them is going to be a capital N, which means no transpose. In that situation, we're going to calculate with the first option that we desired, which is the operation alpha times A times X plus beta times Y, no transpose involved. If transpose is capital T, we do the exact same operation, but instead of A, we replace that with a transpose. We're going to impose the condition that this input variable is case sensitive. It has to be an uppercase N, or it has to be an uppercase T. For those of you that want to have some fun, maybe you want to allow either uppercase or lowercase. In the work that we do together, I'm going to restrict the user to uppercase values only. Now that we've documented our first input, let's go on to the second one. In this case, we're going to have alpha, which is going to be a scalar value stored in double precision. Let's keep going. The third input is going to be matrix A. This is a two-dimensional array that's stored in double precision. This array stores the entries of the matrix used for the matrix vector product. Remember, we have this kind of theme that shows up over and over again. We've got mathematical ideas, and then we've got computer science ideas. In mathematics, we call the structure A a matrix. In computer science, we call it a two-dimensional array. So a two-dimensional array is a computer science model of a mathematical idea, which is called a matrix. And we're kind of specifying that in the documentation. This two-dimensional array has dimensions m by n with m rows and n columns. Next thing we're going to do is recognize that the fourth input is going to be a vector x. This stores a one-dimensional array in double precision. These store the entries of column vector x. There are kind of two choices for dimensions. If the transpose input is capital N, x must have dimensions n by 1, since the number of rows of x must match the number of columns of A in that case. If, on the other hand, the transpose input is capital T, x must have dimensions m by 1, since the number of rows of x must match the number of columns of A transpose. A transpose would have m columns, thus x must have m rows. We move on to the fifth input, which is going to be a scalar beta stored in double precision. If beta is set to 0, we do not need to define the input vector y, since we can do that within the function itself. This gets us to our last input, y. This is going to be a one-dimensional array stored in double precision. We know that if beta is non-zero, we must provide input array y storing the column vector y that we want to calculate with. There are kind of two different choices for dimensions, one of which occurs if we don't want to use the transpose, in which case y must have dimensions m by n, because the number of rows of y has to match the number of rows of A times x, which in this case would be m by 1. In the other case that we want to use the transpose, the dimensions are flipped, so that means that y must be an n by 1. In both cases, the initial value of y is going to be overwritten and updated to store the new value that we want to output. With that, we've documented all of the different inputs that we have to this function. Let's move on to documenting the output. For our desired output y out, there are really two different choices, one of which comes from calculating without the transpose, and the other one comes from calculating with the transpose. Here we see exactly the value of y out that is going to result from the implementation of our function. We know that this is going to be stored in double precision since we're focusing on that in this library implementation. And we remind the users that y out actually stores the desired matrix vector product that we're trying to achieve with this function. We've now customized the input and outputs. We're going to skip the example lines of code for now. We're also going to skip other M files and subfunctions and MATLAB files. We notice that the references are still valid, and we probably want to update this. Today actually is November 17th. So we're going to go ahead and just write November 17th, and we'll say that this is the last revision. Of course, I've actually already written this for myself so that I knew what I was talking about, but we're kind of demonstrating the process of documenting code. In this case, we actually can maybe delete some of this stuff. This is old code that we use for the descale function, and we can delete this. And of course, we know that the y out is going to get the value of y that we actually update in our algorithm. I think we're pretty much ready to get started on this. We've documented and kind of set up the structures that we need to get started coding. Let's go over to the test driver we're going to use. So specifically, the dgemv test driver is going to be a script file used to test and debug the corresponding function, just like we've done in all of our cases. And we already actually have a list of specifications, so we'll replace the previous one from the descale with the updated version from what we've seen earlier. In this case, I'm literally just going to translate the specifications that I've already written up into comments. So specifically, let's go ahead and do that. Remember that the first line is a quick description, so we say that the dgemv function performs matrix vector multiplication in one of two forms. These are the same ideas that we documented in the function file itself. And then this routine satisfies a number of specifications, and we've already read these out loud. I literally just translated those into comments. Remember, as we're doing this, the most important thing is not what I'm saying out loud, it's what you're doing at home. One of the things that I would love for you to do is to create your own function file by following along. One, this will give you an indication of how much time it actually takes to type all this stuff out. And then two, you can reuse this work for other functions that we might want to code in future videos, and also for some of the portfolio projects that you might want to choose in your own experience for this course. Now that we have our desired specifications, let's go ahead and make sure that the rest of this documentation works well. Same idea we're going to use here to properly use this code. Simply uncomment the section that you'd like. This, of course, we're going to actually use the dgemv function file. And perhaps this gives us a good idea that over in that function file, we actually need other M files. So this is going to be dgemv and then test driver.m would be useful, at least in our work. And then, of course, we want to update this with a proper date. So we kind of have this here. Let me just copy and paste. So that makes it kind of really easy. And now we're ready to begin our code. So specifically, we're going to start the same concept that we've done every time, which is to clear the memory and to clear the command window. And then we're going to do error checking.